Hi guys, this is Equilibrium 101, and this is just an introduction to equilibrium and KEQ. And I have forgotten at school my packet and my book that tells me which problems to assign you. So I will have to go to school tomorrow. Hopefully I can get in the building and get it. So we'll say that the problems are to be announced, and that would be the chapter 15 problems. Okay, so let's start with something that we can all recognize, and that is just a regular old reaction where we have reactant A and reactant B, and they make two products, C and D. Okay, so this is just a regular old reaction, and we want to recognize that when enough A and B react to make C and D, some of the C and D can react to make A and B. So it would look like this. We'd have A plus B only going in reverse. Okay, so let's stop for just a second here and label a couple things. We would call this the forward reaction. And this would be the reverse reaction. Okay. So the forward reaction has a certain rate. So when the forward reaction rate is equal to the reverse reaction rate, then the system is at equilibrium. So you can kind of maybe think of an analogy that might help you understand equilibrium. My analogy is always that I come home and clean my house, and then that's my forward reaction, and then my kids come home and they mess it up, and that's the reverse reaction. And there's an equilibrium going on there, that it's always it's always kind of in the same state. You know, the house is sort of like, it's either I clean it up, they mess it up. I clean it up, they mess it up. So anyway, that's just one sort of analogy to think of. You can probably think of your own equilibrium in your own life. And so the way that we show equilibrium, we notate it, equilibrium, with a double arrow. So the way to show this would be A plus B in equilibrium with C plus D. Or you would see A plus B in equilibrium, and this is more common, C plus D. They mean the same thing. And this is just kind of a lazy way to make an arrow, a little half arrow. At equilibrium, I'm going to change colors here just for fun. At equilibrium, the concentration of A, the concentration of B, concentration of C, and the concentration of D are constant. Because they're turning into each other at the same rate. So because A and B make C and D just as fast as C and D make A and B. So kind of like there's always a pile of dishes in the sink because the number of dishes in the sink is always the same because I empty the sink at our house and then the dishes go back into the sink once we eat. So you could think of it like there's just always just a few little dishes in the sink. So that would be analogous to A and B and C and D being constant concentrations. And if the equilibrium is in an aqueous solution, I'm gonna scoot this over here, sorry, is in an aqueous solution, then we use concentrations of A and concentration of B, etc., etc., etc. If it's a gas equilibrium, then partial pressures are used. So partial pressure of A, partial pressure of B, partial pressure of C, and partial pressure of D are used. So it's either concentration in molarity or partial pressure in any of the units of your choice, usually in atmospheres. And so if these are constant, the concentrations or the partial pressures, then we could also recognize that the relationship that is the ratio between them would be constant. So if the concentrations or the pressures are constant, then the ratio between them is constant. So we can say that some constant value would be equal to the ratio of the concentration of C and concentration of D compared to the concentration of A and the concentration of B. So if we compare the concentration of the products to the concentration of the reactants, we get a constant value. Okay, and this constant value has a special name. This is called the equilibrium constant. And this is notated with the letter capital K and then subscript EQ, KEQ. K for constant, of course, because we all know constant is spelled with a K, and EQ for equilibrium, and that is just the ratio between the products and the reactants. So we'll get more into the mathematics of this in part 2. And we want to recognize also that KEQ is a value, is a number, and it's different for every reaction. Sorry, you probably have to blow that part up to see it. So anyway, this is part 1, and I'll come back with part 2 here shortly. Thank you.